Hi, this is an example problem on relativistic energy and momentum from chapter 28. Pause for a moment to read the question. So we have a proton here, and the speed of the proton it's traveling at is given. Now the proton mass is also given to us. It's given to us in units of MeV per c squared, which is a new unit of mass that we often use for small particles like protons, electrons, etc. There's a conversion factor so that we can convert from units of MeV, mega electron volts per c, the speed of light squared. We can convert that between kilograms. In this problem, we're just asked to calculate various properties of this proton. What is its rest energy, its total energy, kinetic energy, and its momentum? Well, we need to use the relativistic equations for these things. So let's start with the energy. So the total energy is the entire energy that an object has, including its kinetic energy, but also the energy it has if it weren't moving. So both of those things. And the rest energy, the energy that it has when it's not moving, is attributed to its mass, but it also includes other things like potential energy, etc. Now, this is equal to E gamma m c squared, where gamma, again, is 1 divided by square root of 1 minus v over c squared. V is the speed of the object, in this case the proton speed. So this is gamma's, again, an easy way to remember this. The rest energy is just equal to mc squared. That's Einstein's famous equation for the rest energy of a mass. Now if we go ahead and write these down, so the rest energy, which we call E0, that is just mc squared. The total energy, E with no subscript, that is gamma times mc squared. And finally, the kinetic energy, well, kinetic energy, again, that's the difference, the total energy, E. If we subtract off the rest energy, we're left with the kinetic energy. And that allows us to write this in another way. So if we plug in the values from above, gamma mc squared for the total energy minus mc squared for the rest energy, we can factor the mc squared out, and we're left with gamma minus 1 times mc squared. All right, so let's go ahead and it says to do this in SI units and units of MeV, mega electron volts. I'm going to start with the MeV since we already have the mass in that units, and I want to show you how easy it is when we work with those particular units. Let me go ahead and just do this below here. So for part A, E0 is equal to mc squared, plug in the mass, 938.272 mega electron volts per c squared. Now I don't even need to plug in the value of c here, because I can just cancel these out directly. And we end up with, okay, that was easy. This is the rest mass of the proton. Now to do the other one's going to be pretty straightforward too, but we're going to need to calculate what the value of gamma is. So let's figure out what gamma is for this problem. Remember, gamma, that's equal to 1 divided by the square root of 1 minus v over c, quantity squared. In this case, that's going to be 1 divided by 1 minus v, 0.95, c divided by c squared. The c's cancel, and when we put this into our calculator, we come up with a value of about 3.20. So there's our gamma. So to do the total energy, all we got to do is multiply gamma times mc squared, the rest energy, right? So that's going to be gamma 3.2 multiplied by the rest energy. You already knew what that was. Which gives us a value of about 3,004.875 MeV. Now to do the kinetic energy, right, it's just the difference between, this is the total energy, that was a mistake there, should just be no subscript, there we go. So to do the kinetic energy, right, it's just going to be the difference between the total energy subtracted from the rest energy, right? We could just subtract these two numbers, in other words. But I'll go ahead and just do it this other way. I'll use this equation here. In this case, it's going to be gamma minus 1 times mc squared. In this case, we know what gamma is. It's going to be 3.20 minus 1 multiplied by mc squared, the rest energy. Again, 938.272 MeV. And when we put that in, that's going to come out to 2,066.603 MeV. And you can check by subtracting the part A from part B that that's exactly what you get. All right, let's look at part D here. We're going to look at the momentum now. This is the relativistic momentum. We need to look up the equation for that. Here it is. And we can see that the relativistic formula for momentum, it's just gamma mv, gamma times the ordinary classical formula that we're familiar with. Again, gamma is 1 divided by that square root, as usual. So we can go ahead and write that down. P equals gamma mv. Now, one way to do this, of course, is to go ahead and just plug in all the numbers. And I'm going to go ahead and just do this first in terms of using SI units. So remember gamma, we already solved for that, 3.2. The mass here, well, let's use the mass that's given, 938.272 MeV per c squared. Now I need to convert that to kilograms. I'm using SI units now. Let's go back and look at our conversions here. So there's 1.6605 times 10 to the minus 27th kilograms per 931.5 MeV. Let's go ahead and put the conversion factor in there. So I put the conversion in there, which says we're going to cancel out our MeV per c squared, and we'll be left with kilograms. And finally, we need to put the speed in there. Remember that that is 0.95 times the speed of light, which is 3.0 times 10 to the 8th meters per second. And when we go ahead and compute all of these numbers together, we're going to get an answer. It's going to be in SI units, and it comes to 1.522 times 10 to the minus 18th kilograms meters per second. That's the momentum of that proton. Very small because that's such a tiny mass. Now I want to go ahead and show you how to calculate that in a different set of units using the MeV. Go back to our equation real quick, our notes here real quick here. In one equation we have called the triangle relation. If we know the energy, we can relate that to the momentum with this triangle equation. Solving for P, we come up with this equation here. We can go ahead and write that down. Let's go ahead and do it. We plug in our values. E, the total energy squared, 3004.9 MeV squared, minus the rest energy squared, 938.3 MeV, square root that whole thing, and divide by C. Now the C I'm not even going to plug in. But if I compute the top number, it comes out to 2,854.6 MeV. And now I'm going to just add that C to the units. And so this is another set of units here for momentum. In fact, you can convert between the two with a conversion factor. Now to go ahead and look at A through C again, now we want to go ahead and figure out what are the values in SI units. I mean, of course, we could go right back to these same equations. We could convert from MeV c squared, per c squared, back to kilograms, we could plug in the value of the speed of light and we could just calculate all the numbers. But instead of that, let's go ahead and just convert directly energy in mega electron volts straight to joules. And to do that, we can see 1 eV is this quantity of joules. So let's go ahead and do that conversion. We'll do it right below here. So if I've got 1 MeV, M is mega, that's 10 to the 6th, that's equal to 1 times 10 to the 6th eV, and we said that 1 electron volt, a unit of energy, is equal to 1.6 times 10 to the minus 19th joules. And if we calculate that, that comes out to about, let's see, cancel the EV, we can do this in our head, it's going to be equal to 1.6 times 10 to the minus 13 joules. So that's our conversion factor. And let's go ahead and just apply this to each of these. So for the first one, I'm going to multiply by 1 MeV per 1.6 times 10 to the minus 13 joules. And of course that'll cancel the MeVs out. We'll be left with joules, and doing that calculation comes out to 1.5 times 10 minus 10th joules. And we can go ahead and use the exact same conversion factor to do the other conversions as well, since they're also energies. And for part B, that calculation comes to 4.81 times 10 to the minus 10th joules. Part C comes out to 3.31 times 10 to the minus 10th joules. And so we can see how to apply those equations for the relativistic energy and momentum.